Hello, welcome to our semiconductor education program. This is Vincent Chang. Today I'm going to teach you how to analyze depletion layer of a p-n junction. Depletion layer, part 1, charge, field, and potential. So before we dive into analyzing the depletion layer of a p-n junction, so let me just quickly review some of the basic concept of the p-n junction. So starting with the depletion layer. And then the process of letting a p-n junction going into the thermal equilibrium condition is this. Starting with the diffusion process, and then the electric field will be created across the junction, near the junction. And then because of the electric field, the drift current, the drift mechanism will be induced. And then at thermal equilibrium condition, these two forces is going to balance, causing the net current equals 0. And then the concept of energy barrier. On the left-hand side, it tells us under the thermal equilibrium condition, the abundant hole on the left-hand side, because the p-type, the majority carrier, is hole. So a lot of hole on the left-hand side are facing rightward, and they see what? They see an energy barrier. So in the same way, on your right-hand side, you see a lot of electron on the right-hand side, and looking leftward, they see the same kind of an energy barrier. So under the thermal equilibrium condition, a lot of the hole on the left-hand side, a lot of electron on the right-hand side. So both majority carrier facing the interface, they see an energy barrier, so got blocked. So this is the thermal equilibrium condition. And then the concept of building potential. So under the thermal equilibrium condition, there's a potential difference across the junction. The electrostatic potential difference across the junction, which is called the built-in potential, and determined by what? By thermal voltage, a natural log, acceptor atom concentration, donor atom concentration divided by intrinsic carrier concentration squared. Now, let's move on to the subject, the core material of this lecture. So charge neutrality in the p-type. If it just think about this, if there is an independent p-type semiconductor, and then charge neutrality will hold. So in the same way, the charge neutrality for the n-type semiconductor, an individual n-type material, and the charge neutrality remains true, right? So charge neutrality for the P and charge neutrality for the n-type material. And then now, the both material forms a junction. So the overall charge neutrality remains true, right? So the overall charge neutrality should be true, should be remain. So in other words, the overall charge for this system, for this p-n junction system, is 0, right? Is 0, should be 0. So which means what? The left-hand side, which means under the thermal equilibrium, although the depletion layer is formed. And then although the certain charge ions nature got exposed, right? So on the left-hand side is the acceptor ion, carry negative charge. On the right-hand side of the depletion layer are positive. So the donor ion. But the overall charge neutrality should be remain. So which means what? The total charge should be 0, which means the total amount of the negative charge on the left-hand side should be equal to the total amount of charge on the right-hand side of the depletion layer. Let me repeat that. The total negative charge on the left-hand side of the depletion layer should be equal to the total amount of positive charge on the right-hand side of the depletion layer. So which means Na minus the negative acceptor ion times the width, the xp. The xp should be equal to Nd plus the positive donor ion concentration times Xn. So let me ask you this. What's the dimension of the Na minus times xp? What's the dimension of this, of the Na minus times xp? Should be, because this 1 over per cubic centimeter times centimeter. So it's the per unit area, right? So 1 over centimeter square. So which means the per unit area. All right, so left-hand side is the per unit area. The right-hand side is the per unit area. So if you put on, I just want to emphasize this. If you put on the cross-sectional area, A on the left-hand side, it becomes the total charge on the left-hand side. And then the A on the right-hand side is also the total positive charge on the right-hand side. And both A got canceled out. So this represents the per unit area, the total negative charge on the left-hand side per unit area should be equal to the total amount of positive charge on the right-hand side per unit area. I just want to make sure, I just want to clarify this, all right? And then now, under the complete ionization, this blue equation is the complete ionization, the assumption. So under the assumption of complete ionization, and then the Na times xp should be equal to Nd times Xn. So Na times xp should be equal to Nd times the Xn. So the majority of the p-n junction in the real world is not symmetrical. The dopant concentration is not symmetrical. This is called one-sided, which means that on the one side, it's going to be heavily doped compared to the other side. So the left-hand side is, let's assume the acceptor atom concentration is 10 to the 18th power. So on the right-hand side is 10 to the 16th power. So now 100 to 1. 18 and 16. So 100 to 1. And then what? Then the ratio between the xp and the xn will be 1 to 100. So again, 100 to 1, and then 1 to 100. So which means the total portion is the 101, and the 1 out of the 101 will be located on what side? Which side? The heavy dope side. So the majority, the 100 out of 101, will be penetrated, will be occupied, will be located on the lightly doped side. Okay? So what's the concept, physical concept behind this? Charge neutrality. So now, the first equation is charge neutrality. The second one is simply the sum of these two, xp plus xn equals the wd. Then based on these two equations, if you solve these two equations simultaneously, then you can get this. Okay? So xn and xp are with respect to the total width, the acceptor atom concentration, and the donor atom concentration. So now, I want to explain this before we move on to the next lecture, all right? Poisson's equation. This is the Poisson's equation. So we need the Poisson's equation to harness, to analyze the electrostatic characteristic or nature of the within the depletion layer. So we need a governing equation to govern the electrostatic nature, the characteristic of within the die, especially within the depletion layer. So here's the Poisson's equation. So Poisson's equation tells us d squared V, the dx squared, the second derivative of the electrostatic potential, equals negative fundamental charge, electronic charge, divided by epsilon s, which means the permittivity of the semiconductor. So times the charge concentration. So this is the Poisson's equation, right? So usually in this subject belongs to the course of electromagnetics. Electromagnetics is a very important subject in electromagnetics. So we just take this and try to apply the Poisson's equation to understand more the electrostatic nature, the electrostatic characteristic of a p-n junction. Okay, that's why we need this. Permittivity, epsilon s. This is the dielectric constant of the silicon is the 12.9. So this is the permittivity of the silicon. So 1.142 times 10 to the negative 12 power farad per centimeter. So now, so what kind of charge present in the semiconductor? So there are two types, right? The first one is the ion, the immobile. The second one is the mobile carrier. Okay? For the mobile carrier, conduction electron and hole. For the immobile ion, the acceptor ion and the donor ion. So 4. Okay? So 2, and then now 4. Positive donor ion, negative acceptor ion. So because it's the negative, you have to put on the negative sign. So minus Na minus. Hole carries positive charge. So plus hole carrier concentration and minus conduction electron concentration. All right? So Nd positive minus Na negative plus P minus N. So how to solve a Poisson's equation? This is the central point of this lecture, okay? Make sure you get this. Starting, if given the charge distribution. Let's say someone give you a charge distribution. And then you simply take the charge distribution and plug into the right-hand side of the equation. And then solve the Poisson's equation, going through the process of solving the Poisson's equation. The Poisson's equation will tell you the electric field distribution. So what's the relationship between the first layer and the second layer? The integration, right? So we just take the integration of the second derivative of the potential will give you the first derivative of the potential. So which is what? Which is the electric field distribution. Okay? So I don't want to belabor the detail of the physical meaning of the negative sign because I taught this before. Okay? So you are supposed to know the physical meaning of the negative sign on the second layer. And then once the electric field distribution is solved, and then what? If you go one step further, then you get what? The potential distribution. All right? So remember this. Charge, electric field, the electrostatic potential distribution. So charge, field, potential. Okay? So now you don't have the excuse to saying that you forget So you said, I forgot everything I learned from the electromagnetics, or I never learned the electromagnetics well, okay? So now, this is the key takeaway of this lecture, all right? Charge, field, and potential. So starting from the charge distribution, let's say if it's the step dial. What do we mean by the step dial? The charge distribution is uniform. The uniform distribution. The donor atom distribution, concentration distribution is uniform. So uniform charge distribution, and then what will be the electric field distribution? Linear, right? Linear. But outside the depletion layer, there's no field because there's no charge. There will be no field. There will be no electric field. Oh, okay. I just want to mention before we go on to the electric field distribution, the area of these two rectangles should be the same. Charge neutrality should be remain. So now let's move on to the electric field distribution. As I just mentioned, outside the depletion layer, no field. So boundary condition. So at the interface, it's going to be the strongest. It's going to be the strongest. Okay? Why is below zero direction? All right? Because the electric field is pointing to your left, which means the electric field is less than 0. All right? So if the electric field is positive, which means the field vector is pointing toward the positive x direction. So now it's pointing toward negative x direction. So less than 0 means the direction of the field is leftward. And then constant after integration, linear, right? Constant, charge, linear electric field. And then if the field is first order, it's a line, and then what about the potential distribution? It's going to be the second order, right? So it's going to be the second order, but I explained this before. And then the potential difference is what? The geometrical meaning of the integration is what? You learn from calculus. It's the area, right? So the area of the triangle represent the building potential. All right? So this is the key takeaway of this lecture. So make sure you understand charge, electric field distribution, and potential distribution, and mathematical behavior, constant, linear, and second order. All right? So this is the end of the lecture. See you in the next one. Thanks for watching.